Right now, time is passing faster at your head than at your feet, not as a feeling, not as philosophy, as a measured fact of physics. One so reliable that in 2010, scientists watched it happen between two clocks separated by a single foot of height. It has been true every day of your life, and by the end of this video, you'll see why the same effect quietly rescues your phone's GPS every 2 minutes. Why 4 airplane seats once held the most important passengers in physics, and why particles that should be impossible are passing through your hand as you watch this. But it starts with a clock, raised 12 inches. In 2010, at the National Institute of Standards and Technology in Boulder, Colorado, a team led by physicist James Chin-Wen Cho built 2 of the most precise clocks ever made. Each one keeps time using a single aluminum ion, one atom trapped, vibrating between 2 energy levels more than 1,000,000 billion times per second. These clocks are so precise they wouldn't drift by a second in over 1 billion years. Then the researchers did something wonderfully simple. They jacked one clock up by 33 centimeters, about a foot. The raised clock ticked faster, not once, not as noise, consistently, measurably faster, exactly as predicted. NIST's own press release put it in plain language. Your head is older than your feet. Over a 79-year lifetime, a 1-foot height difference adds up to about 90 billionths of a second. Your head has been living in the future your entire life. 90 nanoseconds sounds like nothing, but hold that thought, because the question isn't the size of the effect. The question is why height changes time at all. The answer was written down 95 years before the experiment by a man who never saw an atomic clock. Einstein's relativity makes 2 claims about time, and both sound like science fiction. First, motion slows time. The faster you move through space, the slower you move through time. One way to hold this in your head: everything in the universe travels through space-time at one fixed rate. Stand still, and all of that motion flows through time. Speed up through space, and something has to give. Time is what gives. Second, gravity slows time. The deeper you sit in a gravitational field, the slower your clock runs. Not your perception of time, time itself, chemistry, biology, the vibration of atoms, everything. Your feet live deeper in Earth's gravity than your head, so your feet, right now, are aging slightly slower. The NIST clocks didn't create that strangeness. They just finally built an instrument fine enough to catch it. And if this all still sounds like an abstraction that only matters to atomic clocks in Colorado, it isn't. You almost certainly use both of these effects today. They're the reason a map on your phone knows where you are. 20,000 kilometers above you, GPS satellites are flying at nearly 4 kilometers per second, each carrying an atomic clock. Your phone finds you by comparing time signals from several of them. And here's the thing, light crosses about 300 meters in a microsecond. If those clocks drift by even a millionth of a second, your location is wrong by hundreds of meters. Now watch relativity attack the clocks from both directions at once. Because the satellites are moving fast, special relativity slows their clocks. They lose about 7 microseconds a day. But because they orbit high above Earth's gravity, general relativity speeds them up, a gain of about 45 microseconds a day. Gravity wins. Net effect: the satellite clocks run fast by roughly 38 microseconds every day. Uncorrected, that would poison your position fix within 2 minutes, and the error would grow by around 10 kilometers per day. Within a week, your phone would place you in a different city. So engineers cheat with Einstein's blessing. Before launch, each clock is deliberately detuned to tick slightly slow, 10.22999999543 megahertz instead of 10.23. Then they launch it into orbit, and relativity itself bends the clock to exactly the right speed. Every time your phone finds you, that's not just satellites working. That's the theory of relativity holding your map together in real time. But maybe you're thinking, that's engineering. Has anyone just taken clocks on a trip and watched time bend directly? October 4th, 1971. A physicist named Joseph Hafele and an astronomer named Richard Keating walk onto a commercial airliner with 4 cesium beam atomic clocks. Their entire budget was $8,000, and $7,600 of it went to airline tickets. The plan: fly the clocks all the way around the world, first eastward, then westward, and compare them to reference clocks at the U.S. Naval Observatory in Washington. If Einstein was right, flying east, with Earth's rotation, the clocks should come home having lost about 40 nanoseconds. Flying west, against the rotation, they should come home ahead by about 275. The eastward trip took 65 hours. The clocks came home behind, 59 nanoseconds plus or minus 10. The westward clocks came home ahead by 273 plus or minus 7. Prediction met in both directions with the cheapest experiment in the history of testing spacetime. Time on an airplane genuinely runs differently than time on the ground. Not felt, measured on a machine you could buy tickets for. Still, clocks are human machines. Maybe you'd trust the universe more if it ran the experiment itself, with no scientists involved. It does, constantly, right above your head. When cosmic rays slam into the upper atmosphere, kilometers above you, the collisions create particles called muons. A muon is unstable. At rest, it survives about 2.2 microseconds before falling apart. Even moving at nearly the speed of light, that lifetime buys it roughly 660 meters of travel. The atmosphere is many kilometers thick, so essentially no muons should ever reach the ground. That's the classical prediction, and it is spectacularly wrong. Hold out your palm. About once every minute, a muon passes through each square centimeter of it. Detectors at sea level count them around the clock. They arrive in enormous numbers, particles that, by pre-Einstein physics, should not exist down here at all. They make it because they're moving so fast that, from our point of view, their internal clocks run slow. 2 microseconds of muon time stretches across the whole journey. And here's the beautiful part. From the muon's point of view, its clock is perfectly normal. Instead, the atmosphere itself contracts, the distance shrinking to something it can cross in time. 2 completely different stories, the same muon in your palm. Both true, depending on where you stand. That's not a bug in the theory, that is the theory. We grow up picturing time as a river, one current carrying everything and everyone along at the same rate. Every experiment you just saw says that picture is wrong. There is no master clock. There is no universal now. Time is local. It runs slower near mass, slower with speed, and no 2 paths through the universe ever quite agree. Earth's gravity is gentle, so the disagreements around you are nanoseconds. But they are everywhere. The core of the Earth is younger than its crust. Mountaintops age faster than valleys. Every satellite, every airliner, every particle is keeping its own, private, perfectly correct time. You are not moving through time like a leaf on a river. You are a walking stack of clocks. Heart, head, feet, each one shaped by where it sits and how it moves. None of them in perfect agreement. All of them right. So the next time your phone finds you on a map, remember what's actually happening up there. 38 microseconds a day, deliberately misset clocks. Einstein in the loop. Your head and your feet have never agreed on what time it is. They never will. If that bent your intuition a little, that's what this channel is for. The universe doesn't match the pictures in our heads. That's the best thing about it.